Okay, why don't we go ahead and get started. So today, Howard Bushouse is going to tell us about the JWST calibration pipeline. Go ahead.
Okay, welcome everyone. Even though obviously my name is the only one on the title slide here, obviously rest assured that this is all based on the input of many, many dozens of people. And in particular, I need to give a shout out to Carl Gordon, who's the current lead of the calibration working group here at the Institute. He actually helped supply a lot of the material for this presentation. And as we'll see later on, they're the group that's really setting the direction of a lot of the pipeline development itself. So, okay, I can't get my slides to advance. That's a good start.
Just if you click on the mouth. Yeah.
Okay. So just a quick outline. A lot of this is going to be fairly high-level material. If you're interested in the details of how specific calibration algorithms work, you're going to be disappointed, at least as far as today's presentation is concerned. There isn't enough time to go through all of that. So we're going to focus primarily on just the overall philosophy of how the pipeline is being developed, the kind of user experience we're shooting for, how various groups are deciding what goes into the pipeline, sort of organization and structure that we're giving to the pipeline, the kind of data products that users will be receiving, the way we're going to make the pipeline available, and at the very end, just a little taste of a few details here and there. So throughout this whole process, which started 4 or 5 years ago already, we've actually been working on it for quite a while. We're trying to, not reinvent the wheel. Don't want to just stumble around from scratch blindly. We're trying to take advantage of everything that's been learned, not only from here at the Institute with previous support of Hubble, but also support of other observatories like Spitzer and Herschel, and as well as experience from other ground-based observatories and instruments, especially when it comes to observing modes that are completely new for JWST, compared to HST, things like interval field spectroscopy and multi-object spectroscopy. We've never dealt with anything like that in any of the HST calibration pipelines, and so we're trying to take advantage of collective knowledge, the community who have had experience with that, so trying to figure out how to do things, and in some cases, how not to do things. So at a very high level, what's being implemented in the pipeline in terms of the actual calibration algorithms is being based on essentially cherry-picking what's decided to be the best or most appropriate methods based on input and that experience of other instruments and all of the JWST instrument teams together, as well as people who are experts in specific observing modes. So that our goal, obviously, is to provide the best algorithms that have been looked at and examined by a fairly large group and decided that, yes, this is the best unified approach to take for JWST. We're also trying to do a lot of code sharing as much as possible between the JWST instruments. Unlike the HST calibration pipelines, where you had an independent pipeline for each of the instruments on the telescope, here we have a much more unified approach where a lot of the same algorithms and code are applied to all the different instruments, at least where it makes sense to do so. It makes it a whole lot easier to develop and maintain. It's also much easier for our users to make use of, to be able to apply the same kinds of things to data from all the different instruments. And of course, as always, we have high-level goal of providing that pipeline directly to the community, as we've always done in the past with previous pipelines, so that you can play along at home if you like. So in terms of our user experience and what you'll be getting from the pipeline, when data first hit the ground from the telescope, the calibration pipeline will be run in a highly automated environment on all of the data. Because it is an automated environment, it will have to use default parameters and settings for the various things that it does, since no human interaction is available at that stage. And so we will then provide default products coming out of that pipeline that will have gone through what we think is the best or most appropriate processing that can be decided in an automated fashion. And you'll get not only final calibrated products, but raw and intermediate products will be available as well. And as I just mentioned previously, users can install and run the pipeline locally as well to allow them to tailor processing to specific observations, places where the defaults that were chosen in the automated environment need to be tweaked a little bit to increase the scientific return for their particular data. And also something that the JWST pipeline will give you is that there will be automatic connection to or access to the calibration reference data system here at the Institute, which will enable you to get all of the necessary calibration reference files that are needed for processing, things like darks and flats and whatever. Those are provided via a web service. So if you've got an internet connection, when you're running it, it'll either simply access that data directly across the web, where the data reference data files are physically sitting here at the Institute, or if you like, you can choose to have the system download copies of them locally for your use on your own system. And just a quick few words about the distinction versus what's going to happen in the automated pipeline versus how it relates to data analysis tools. As we said, the pipeline is going to run in a highly automated fashion, doing things the best it can without any human interaction to tell it, what's the best approach for each particular observation set. So that's where then the connection to data analysis tools come in after that, where you're doing the kinds of things that really do require human interaction. And naturally, there is some amount of overlap between the two. For example, some steps or parts of the automated pipeline will essentially be the same algorithms or tasks that are made available as part of the data analysis package as well, so that it's then easy to rerun things if you want to, again, optimizing as you go. So the way all of this is being designed and decided as to what gets implemented follows more or less the organization that you see here on this chart. We've got people from all of the JWST instrument teams, as well as some specific working groups that have been set up that span multiple teams or even multiple institutions to concentrate on specific observing modes. Like there's a coronagraphic working group that deals specifically with time series observations, one that focuses specifically on moving target observations. And so we collect inputs and knowledge and proposed algorithms from all of those teams, which get delivered to or presented to the calibration working group here at the Institute. Their job is to collect all of that information, review it, discuss it amongst all the representatives of the multiple teams, and arrive at a decision as to which approach is the best, which algorithm should we choose, just to get everyone on board in terms of deciding what's the appropriate way to do something. Once that decision has been made, that information flows down to our data management system working group, and that's a group of people who dig more deeply into the details of, okay, how are we going to actually implement these algorithms, how we figure out connections to the different subsystems of the ground system that are needed to do it, that sort of thing. And finally, then, all that information flows down to people in the science software branch who are doing the majority of the actual coding to make it happen. Now, at least this is the official theory of how things happen. We all know that in reality, it often tends to look a little different. There's a lot of two-way interaction between the various teams in terms of sharing information and asking questions and trying to figure out details. But in the end, we do end up eventually with consensus and direction from everyone as to what finally gets implemented in code. So our plan over these past several years for doing all of the development work arrived at sort of two different versions of the pipeline that we will come out with in the not too distant future. The first one that we're working on right now, which we're referring to as the baseline pipeline, consists of algorithms that cover all the instruments, all the observing modes, to provide science products that are deemed to be good enough, adequate to start doing science on as soon as science starts actually flowing from the telescope. These algorithms also are designed to meet any project level requirements that were imposed on the whole calibration pipeline. So we're now at a point, as of today, where 99% of those algorithms have been defined and decided on, and many of them have already been implemented. We're in the process of finishing up our last sort of build cycle in that implementation process. That process will be finished by the end of this year. Final testing of that complete baseline version of the pipeline will then start happening immediately next year in 2018. Of course, that won't be the end of the story. That's just enough to cover what we need to cover to get us flying, or as soon as data starts coming down during commissioning and first release science observations. As soon as that work is done, we will then immediately dive into starting work on what's being referred to as the optimal pipeline. Go back and implement more sophisticated algorithms than what was in the baseline. There are already some optimal algorithms that have been decided on that we will start implementing next year already, even before launch has taken place. But then obviously, once launch does happen and we start getting data in about a year and a half from now, there's obviously going to be a lot of continued and ongoing work after that time. I know it's never happened before with other projects that you ever had to go back and fix things once you actually start getting data from the telescope, but I have a sneaking suspicion we just might need to do that in this case. So there will definitely be more to come for many years yet. Okay, the way the pipeline is organized, as I mentioned back at the beginning, for anyone who's used to working with HST data, we have a separate kind of monolithic pipeline for each of the various instruments. Well, we're taking a very different approach with the JWST calibration pipeline. it is being organized more by observing modes as opposed to instruments. So you'll have routines that are specific, for example, to imaging, as well as routines that are specific to different flavors of spectroscopy and pornography and aperture masking interferometry and so on. It's also at the same time organized by different levels or types of calibration. For example, there are correction steps that deal only with removing and correcting for detector artifacts. And then there are the kind of steps that do actual calibration of the data, steps that do things like background subtraction, and then others that combine data across multiple exposures and spectral extraction operations, that sort of thing. So if you look at this list, you might note that if you compare this to what we currently do for a lot of the HST instruments, this is a pretty ambitious goal we've set for ourselves. Not only are we going to be including processing of several types of observing modes that we don't even have on HST, things like integral field spectroscopy or aperture masking interferometry. These are all totally new, but we're also including and calibrating modes within the automated pipeline that we don't currently include in some of the HST pipelines. Like, for example, if you've ever obtained wide field slitless spectroscopy from wide field 3 or ACS instruments, the calibration pipelines only took you so far. They got you to a pseudo-calibrated individual exposure, but then it was up to you to go off and use some other package like the AXI package to finish the reduction and calibration of that data. Same thing with pornography. That's available on HST, but we only take it up to a certain point, and then it's up to you to do fancy things like PSF subtraction and so on. We are going to include at least default versions of all of that processing in the JWST calibration pipelines.
You mean you're also like doing PSF subtraction in images?
Yes. Yep.
So you're like providing a catalog of like objects.
Right. That'll be doable in a couple of different ways. Like observers, when they take the coronography observations, they can, if they want, also specify additional observations of a PSF reference target. And if they do, then the pipeline will know about that, and it will use those PSF reference observations to feed into algorithms that do the PSF subtraction for you. Also, at the same time, there are plans to build up in the archive or in CRDS like a PSF reference image library. Of course, that'll take some time, to gather those observations. Then once that's available, there's also the option of using that library of PSF images to do the PSF subtraction. Okay, so in terms of the organization based on the type of calibration activity, the pipeline is basically broken into 3 major stages. The first stage deals primarily with just removing detector artifacts and also collapsing your raw ramps of readouts of the detectors into count rate images for you. At the second stage, those count rate images then go through some additional operations and calibration, including some things like background subtraction where appropriate and so on, to result in a fully calibrated and corrected individual exposure at the end of that stage. Once you've got all of those fully calibrated individual exposures, stage 3 of the pipeline then kicks in and does whatever operations are necessary to combine data across multiple exposures. Things like, combining your dithers and combining images into mosaics and all sorts of operations like that. So when you combine those two types of organizations based on observing mode on the one hand, as well as type of calibration activity on the other, you basically end up with a sort of matrixed organization to individual pipeline modules where there's one unified stage 1 module that is applied the same way to every exposure, regardless of observing mode, that is just there to remove detector artifacts. Then things start branching out a bit depending on the observing mode. If it's imaging, it goes to a stage 2 imaging pipeline. If it's spectroscopic, they go to a stage 2 spectroscopic pipeline. And even in those, within these pipelines, there is, some branching logic in there to handle observations from different observing modes in special ways. For example, IFU spectra have to be handled a little differently than multi-object spectroscopy exposures from near spec and so on. And then going into stage 3, you get even more specialized branching where things that are just simple direct imaging go into a Cal Image 3 pipeline. Coronagraphic observations get their special processing to do things like PSF subtraction. Aperture masking interferometry likewise gets specialized processing to calculate fringe parameters and so on at level 3. Time series observations are handled in a special way at level 3, as well as all the different flavors of spectroscopy. Ultimately, of course, all of this flows in to the archive. Okay, next few slides, I'll just give you a quick high-level flavor of what's actually in some of those different stages. Again, I'm not going to get into any of the details of how any of these work, and a lot of these don't even include all the steps. Some of them, there are just too many steps to even mention. But for example, at the first stage, detector processing, it's the kind of things you would expect. Flagging of bad pixels, looking for and flagging pixels that have saturated, subtracting a super bias, doing corrections to the data based on analysis of the reference pixels on the detectors, linearity, dark, a correction for persistence, cosmic ray detection by looking for jumps in the ramps of each integration, and finally doing fitting to those corrected ramps to give you a count rate image for each integration or each exposure. Moving on to the stage 2 pipelines, again, just a bit of a flavor here as to what's going on the imaging side, well, both sides for imaging and spectra. We first completely populate a world coordinate system object, and what this means beyond those 3 words that you see there is not just the pointing information. We've already calculated the pointing information for each exposure, but this is a step that then goes in and loads all of the things like distortion models and so on for each instrument and each detector to create a full WCS object that's associated with the data, from which you can do all the transforms that are necessary back and forth between detector space and sky. And for instruments like near spec, you can do transforms back and forth between detector space and the micro shutter plane, as well as then from the micro shutter plane to the sky, and vice versa. So all the information that's needed to do those transforms, which are needed later down in subsequent steps, is all computed and populated at that level and stored with your exposure data. Then allow for things like background subtraction to happen. This kind of background subtraction is of the variety where say on the spectroscopic side, an observer dithered the target within a slit, and so you can just subtract the two images from one another to accomplish background subtraction, or they can observe dedicated off-target background exposures if they want, in which case those exposures are subtracted from one another. So the more typical extraction level of background subtraction for spectra is also available, but later on in the pipeline. This level is strictly one image minus another. So for imaging, we also obviously apply things like flat field corrections, apply flux calibration information to put the data into physical units, and then we also run a drizzle on it to supply you with a rectified version of that image. There are a few extra things that we do with spectra. For example, in the case where you've got observations that have multiple sources in them, like from near spec MOS mode or wide field slitless modes, we'll go out and find all those individual spectra and extract them into their own individual cutouts, and it's then those individual pieces, one piece for each source, that proceed through all the remaining calibration steps, which again consist of things like flat field corrections and flux calibration and a few special things for spectroscopy like aperture corrections and so on. And then again at the end we provide a rectified 2D image of that data and also produce a one-dimensional extracted spectrum. Now keep in mind, all of this processing up to this point is all for a single exposure. And so, for example, things like the rectified images and extracted spectra, it's just the data from one exposure, which is actually kind of a dead end in the processing at this point. Those data are not used subsequently further downstream in the processing. They are simply provided as like a quick look for the user if the user just wants to see what an individual exposure looks like. Because once we get to the level 3 processing where you're combining data from multiple exposures, you don't want to be combining data that's already been rectified or extracted. You want to start from the original data. Okay, so speaking of the level 3 processing, again, just sort of brief highlights of the kinds of things that happen for imaging and spectra. For imaging, you can refine the offsets by correlating source catalogs across multiple exposures. You can do things like background matching, another round of outlier detection in case not all the cosmic rays were caught in the ramp processing step. And you then combine those data into a single mosaic rectified image. And we also then produce source catalog for you from that combined final image. Similar things on the spectroscopic side, background matching, outlier detection, combining the data across multiple exposures where appropriate. In some cases, for all the slit type modes of spectroscopy, that results in a combined 2-dimensional image. For the IFU modes, it results in a 3-dimensional rectified data cube. And then, of course, finally, at the end, we again produce 1-dimensional spectra. Now, since all of this processing is being applied to multiple exposures, it relies on the concept of data associations in order to know what exposures to work on. Even use that in some cases back at the level 2 processing. For example, in the background processing step, the association information tells the pipeline which images are the background images and which are the science target, and that's how it knows which ones to subtract from one another. And then at level 3, the associations tell it which exposures to combine together. For some of the other modes, it tells it which coronagraphic observations are the PSF observations versus the science target. So it obviously needs to know all of that to know how to apply the processing. Okay, the kinds of data products that the user will get for the imaging side, as I just mentioned, level 3 processing results in a final combined mosaic of all the exposures that belong to an observation of a given field or given target. Will obviously be a rectified image presented to you in SCI coordinates. We also make available catalog of sources. Catalog tells you all kinds of things about each source, various parameters of size, shape, some crude photometry, and so on. We also make all of the intermediate level exposure products available, ones that were fully calibrated and corrected in the earlier stages of processing, and those will be made available both in the original distorted detector space as well as in rectified space. So, for example, you can tell these slides came from Carl, who's a MIRI person. So he put together this nice slide on an example of a MIRI imaging mosaic, taking 12 exposures in one of the predefined dither patterns, and they get combined into this final mosaic image. And part of the data product that you get also includes things like a weight map, a coverage map that shows you the relative amount of data that went into each pixel of the image. Kinds of things you're used to if you're used to working with products that come out of the drizzle task. On the spectroscopic side, for both the slit and slitless modes, we provide, again, the rectified two-dimensional images. And again, for those modes that involve multi-objects, like the near-spec MSA and the wide-field slitless modes, you will get two-dimensional rectified combined images for each individual source that was extracted out of the observation. For IFU data, you can get a three-dimensional spectral cube, which has been rectified and put into this linear coordinate system of RA, DEC, and wavelength. You also get the one-dimensional extracted spectrum for each source. There is some variation in processing applied when doing the extraction based on whether the pipeline thinks it's a point source or extended source, and it can get some of that information from upstream in the ground system. Like, for example, the user for some modes can specify via the APT template whether they think this source is point or extended. Or for, say, for example, the wide field slitless modes, where you never know what you're going to get ahead of time. You're just going to get anything that shows up in the field. We run the source catalog on direct images of the field that are taken in conjunction with the GRISM images. And so there you rely on information from that source catalog to not only tell you what sources you've got to work with, but it can also tell you, whether they seem to be extended, and if they are, what's their orientation on the sky, and so on. So that information can then be used in tailoring exactly how the extractions are done. And again, we provide the intermediate exposure level products as well that are fully corrected and calibrated. So here's another example in pictures, again from the MIRI IFU. You've taken individual exposures in all 4 of the MIRI IFU channels, as well as each of the 3 wavelength subbands of those 4 channels. You're going to end up with a resulting cube from all of the channels and subchannels merge together into a single final output cube. For chronographic data products, as I mentioned earlier, we're going to do, in terms of the final data products, will be co-addition and combined image that is a result of having run PSF subtraction on all the individual exposures, as well as then combining multiple exposures of that target, like if you do the common thing of taking exposures at different roll angles on the sky and so on. Those will all be combined into a final co-added product for you. And again, as with all the other modes, you also get the individual integration or exposure level products. So again, picture, I like pictures better than text. Take an example of chronographic observations where you've got your science target, and this is your reference star. And of course, looking by eye, you can't hardly see any difference there. But once those go through something like the CLIP algorithm to do the PSF subtraction, you end up with some interesting sources there in your field. For the aperture masking interferometry mode of the nearest instrument, level 3 processing is going to give you tables of the closure amplitudes and phases and the fringe amplitudes and phases that are computed from those exposures. And also there, you have the option of specifying reference target exposures. If those exist, then these parameters for the science target will have been normalized or corrected by the closure amplitudes and fringe amplitudes of the reference target. And then also a reconstructed image based on those fringe parameters. For time series observation, the final products that you'll get, in addition to the integration level data that we've seen before, for imaging mode time series observations, you will get a final table of photometry of the source that's in the image. Photometry will be as a function of time for all the individual integrations or exposures that were taken on that source. So you can then do any kind of analysis of that photometry as a function of time as you wish. On the spectroscopy side, you will get an extracted spectrum of the source for every integration that was taken. So this can mean, thousands and thousands of spectra if it was a long time series observation. And then we will also provide what we're calling white light photometry, which is basically just taking each of these extracted spectra and just integrating them over wavelength into a single flux value, and which will then produce a similar table that you would get from imaging mode, just total flux as a function of time for that source. Okay, so in terms of the availability of the pipeline and a little more characteristics of the code itself, the whole thing is being written in Python, and we're taking as much advantage as possible of interfacing to and making use of libraries out of existing places like the AstroPy Python library. That's where we're doing a lot of our routines that need to work with world coordinate systems. We're using the JWST library out of AstroPy. A lot of the routines that do source photometry is taking advantage of routines in AstroPy. So we're trying to make as much use of that as possible. It's going to be freely available to everyone. Yes, you don't have to pay us, such a deal. As I mentioned earlier, it will be configurable Each step in each pipeline will have its own configuration file that allows you to set parameters to non-default values if you want. That can also be done interactively with the individual steps and pipelines, so that you should fairly easily be able to rerun all or part of the pipeline on data as necessary. Due to the way it's written in a highly modular way, it's also pretty easy for users to completely replace a specific step if they want. If they think, hey, I have an algorithm that works a little better in my specific data, I'm going to replace the spectral extraction step or whatever with one of my own. The code itself is being hosted in a repository on GitHub. So if you've got a GitHub account, you can actually look at the code if you're kind of into that thing. It'll be distributed and installable to users using Conda. It will be available on the Institute's Astro Conda channel. For doing that, it isn't there yet because we haven't gone public with it yet. Right now, it's in kind of a private Conda area until we come out with, we're hoping, the first public release sometime in the first half of next year. As I mentioned earlier, this baseline delivery of the pipeline that we will be finishing by the end of this year is going to start undergoing testing at the beginning of 2018. And so once that testing has completed and we feel safe, we will then come out with the first publicly available release to the community so that people can start playing with things, get their hands on it for a few months before they actually start getting data. So finally, I'm going to give you just a taste of some of the slightly lower level details in terms of how things are implemented, and coding methods, and so on. Each calibration step is implemented as a Python class, and so it's very easy to call it yourself if you want to from within a Python environment to do anything you want to it. The pipelines are simply just lists of those individual steps that are strung together in a logical way. You can run either of them from the command line of your computer or from within an interactive Python shell or something like Jupyter Notebook. Another interesting or new feature of the way the pipeline is organized is that we're making use of a data model library. And what that basically means is there's kind of a wall or a fence between the user and the actual FITS files that sit on disk. You don't need to know anything about how the extensions of the FITS file are organized or named, how to use PyFits to open them and load it. The data model software library does all of that for you, and I'll quickly show you an example on the next slide. It's one simple command to just open and load an existing data file that you want to work with. And like I said, you don't have to know anything about the actual contents or organization of that file on disk. It's the data model has schemas that tell it all of that information, what the extension names are that I should be looking for, what the data types are of each of those arrays, and so on, and then presents it back to the user in an object that has all of those various data arrays and so on accessible as attributes of that Python object. So just to end up with here, just a really quick example of some actual commands. Say you've got a count rate image you want to run through stage 2 of the pipeline processing. You want to do it from within an interactive Python environment. You simply import the stage 2 image pipeline from the JWST package. You make use of the call method on that pipeline, feed it the name of your count rate image, and it's going to go and do its work and return a new object to you that is the calibrated version of that data. So you look at that calibrated image, something doesn't look quite right, or say you want to do something a little different. Okay, let's make some changes to it. I want to go back to my original input and do some fiddling with it. So you just import the data models library, again, from the JWST package. You now just use this generic open function from the data models library, again, giving it your input file name, and it reads that file, loads it all into a data model that's returned to you as a Python object. That object now has all kinds of attributes or members in it that you can access. Let's say for some, these are obviously stupid or unrealistic use cases, but it's just to give you an idea of how you can access things. Oh, all of the pixel values are too low by 5%, so I'm going to multiply them all and scale them up. And oh, I see there's a bad column of data, at column 500 in the image, so I'm going to set data quality flags for that whole column so that those pixels get rejected. And for some bizarre reason, I want to fake the pipeline into thinking this is actually an F160W image when it really wasn't to begin with, because I wanted to use the F160W flat field or something like that. So you also have available to you all of the metadata associated with the exposure. It's organized in a hierarchical tree underneath that meta object contained in the data model. And so you can change those values, examine them, do whatever you want with it. Okay, I've now made all the changes I want to make. I want to save that just so I don't lose it. All you have to do is call the save method on the model, give it a file name to save it to. It goes off and writes all of that data to a new version of your FITS file, and you feed it back into the pipeline again to redo your results. Okay, so that's all I have for this morning. I'm willing to entertain questions.
Can start with the room. Does anybody in the room have questions?
I'm not sure I can answer them, but I'll entertain them.
I can ask one. So you mentioned about chronography. If there's, for example, a roll between the two, there could be a significant amount of time between those two rolls.
Yes.
Does the pipeline know how to handle this? Does it wait for the second one to do the roll combination?
Yes, it does, and yeah, that happens in a number of situations, not just chronography, but chronography might be the worst case where you really wait a long time to get that additional roll angle. It will, well, what it'll do is you'll end up with processing that kind of happens twice in two different stages. When that first set of observations hit the ground, it'll recognize that it's got all the exposures from the first roll angle to work with, and it'll build an association table out of them and send them through the processing, and you'll get whatever result you can get from the data from that single roll angle. 6 months later, when the data from the second roll angle hit the ground, it'll go through again, and it will then automatically see via our association pool mechanism that, oh, these new exposures actually need to be combined with and processed with these old ones that we also had sitting here from 4 months ago. And so it'll create a new version of the association table that now contains all of those exposures and send it through the processing again so that your second pass results now include both sets.
Will it keep both versions, or does it overwrite the?
I believe that it overwrites, yes. At least in terms of how archiving is concerned, yes. We had toyed with the idea of keeping multiple versions, but amazingly enough, got into enough use cases, it was determined that the logistics in doing so were just so insurmountable that we kind of gave up on the idea, at least for now.
Presumably you can manipulate the association table, a user could, and
yes,
enforce
association tables, unlike for HST, which are in the form of fits tables, and yeah, they're editable, but you know what a hassle it is to edit fits tables. The association tables for JWST are going to be in JSON format, which is at least ASCII text. Yeah, there is some syntax you have to pay attention to, but it is relatively easy to edit that with just whatever editor of your choice. And you know, if you want to exclude an exposure or throw in a couple of new ones, you can freely edit that table and send it back through processing again.
Howard, the typical user may have a relatively rare encounter with this process because you get your data, you spend maybe a couple of weeks, 1 month, and then next year you meet them again or something different. Which means that maybe all the options that you may have, flag this, do that, undo, it gets sort of hard to remember and play with.
Right.
This is the typical case where graphic user interface to the pipeline may be interesting for many people. So you start cal detector, tac, 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 you click, you see your options. Some way to facilitate this. Do you think in your experience is something that could be done, or is this too complicated and out of scope?
I have definitely thought of approaches like that for several years now, realizing that that would be a great thing to have eventually. There are currently no plans in the pipeline, so to speak, right now to implement that. But yeah, once the baseline version is done and we're into the optimal phase of doing things, I think that's quite feasible. And that way, you know, it would be nice to then also have something available in that interface that would allow you to just say, okay, save all of these configurations that I've just set, save it off to, like you can do with the teal interface that we have to tasks right now. It not only allows you to manipulate them, but then you can save them for later. If
you can move from one way to the other one, because the file, you use this same configuration files.
I mean, you can already do that to a certain extent using these configuration files that control each pipeline step or each pipeline module. But yeah, it's up to you to make sure that if you have changed settings in that configuration file, you better make sure to save a copy of it so that it stays there, so that, you know, next week when you come back and start processing some different data and you change it again, you haven't now lost, you know, your settings from the data you were working on this week. But that's sort of a, poor man's approach to doing it.
If there's no other questions in the room, are there any questions online? If there are, could you please go ahead and unmute yourself and ask your question? I guess there's no more questions. All right, so let's thank Howard again for his nice talk. And the next JWST community lecture will be in 2 weeks. All right, thanks everybody.